All right, getting into worksheet B of the first part of chapter 7. So we're going to be looking at 1 and 4 in this video. So starting off here with number 1. So starting off with a given parabola. So find an equation of the normal to the parabola at point A with the coordinates of 3, 0. So this was something we did quite a bit in worksheet A on. So pretty straightforward on this one. The equation of a line. So we're looking for point slope. We already know the point. We just need a slope. So in this case, remember the word normal means perpendicular. So anytime we want to get a slope, that's going to come from our derivative. So if we take the derivative of the parabola, so 4x to the first minus 11. So if we sub in our x value, that's going to give us our slope. So if we stuck a 3 right there, we'd be looking at 12 minus 11, which is 1. So perpendicular to that would just be negative 1. So we got our point, we got our slope. We can just now plug that into the point slope formula to get the equation of the normal. So if we do our y minus y and our slope times x minus x. So a little cleanup on that, and we got the equation to the normal. And again, that's just one format for a way we could write it in, y equals mx plus b. It doesn't specify the format, so we can put that in any format we want. So moving on to part B, show that the normal at A meets the parabola again at point B with those coordinates. So they are asking us to show that this equation intersects this function twice, which just means we can set them equal to each other and solve for x. So in this case, I'm going to take see if I can use what I already have written down here. So I'm going to take the equation of the normal, I'm going to set it equal to the parabola. And we're just going to figure out that point of intersection. So now we're just solving for x. In a case like this, you could certainly solve it by hand. We're just solving in a quadratic, so I'm going to put everything onto one side. So if I add x over, I'm now to negative 10x. If I subtract 3, I am now at 12. If I divide out the 2, that would make life a little easier for me. Oops, that's a minus right there. So now I could easily solve that by factoring. So if we did x minus 2, x minus 3. And keep in mind, we already knew one of those solutions should have been 2, because that was the one that one of those should have been 3, because that was the one we were already given right here. So we already knew one of the solutions should be 3. We were finding the other point where they intersect, which is point B, and so that must be the 2. So again, we already knew that answer. That one's already been used. So this must be the other point of intersection. So we're using the x-coordinate of 2. Just an FYI, if you wanted to do this in your calculator, you easily could. If you were to graph this line as one equation, graph this parabola as a second function, so you got 2 graphs on the same screen. Under Calc on your calculator, there's an option that says intersect, and you can use that to get the 2 points of intersection. One of them you would already know. You would simply be finding the other point of intersection, which would be this one. One thing you got to keep in mind in this problem, though, is it said show. So in a show question, you have to show the work. We already know the answer, so it's not enough to just use a calculator to get the answer. We already know the answer. They're asking us to show the work for where that comes from. So that's what we're doing here, is showing that work. Obviously, now that we have the x-coordinate, I can plug that back into either equation, either the original function, the parabola, or the equation of the normal. Where'd it go? The equation of the normal, which was the negative x plus 3. So I could plug it into either place to get a y-coordinate. Obviously, he's easiest, so if I took my 2 and put it right there, I have negative 2 plus 3, which would give me 1 for the y-coordinate. So at 2, 1. We now have the other point of intersection that they're calling point B. All right, moving on to part C. So now we have the coordinates of the point C. So maybe we got a third point going on here. On the parabola at which the tangent line is parallel. There we go. which the tangent line is parallel to the line AB. So if we look at the 2 points that we already have for AB, so we got the 3, and the 2, 1. So if you look at those 2 points, so if it's parallel to line AB, well, that just means we first need to know the slope of AB. So if we do the little slope formula, so if I did y minus y over x minus x, so you can see on this one, our slope is -1. So if I want a line that's parallel to that line, that just means it's going to have the same slope. So we already know the slope's going to be -1. They're going to have the same slope. So I need coordinates for point C that with this slope of -1. And as always, slope means derivative, or gradient means derivative. So in this case, I have my derivative, which was 4x minus 11. I can set that equal to my gradient in order to solve for x. So if I add the 11 over, divide by 4, and we got 10/4, or 5/2, or 2.5, however you want to write that. Scoot that up a little bit. So there you go. So we got the x coordinate, and it does say coordinates, so I do need an ordered pair for this. So if I take my 5/2 and plug it back in to the original function up there, I can get my y coordinate. Remember, it's a point that is on this function, so this is the one we need to plug into in order to get a y coordinate. When we were doing the one earlier, we were talking about a point of intersection. So this point, point B, is the point where this line meets this parabola. So it's a point that is on both functions. So that's why it didn't matter which one I plugged it into. I would get the same y coordinate in either case. But for the one we're talking about right now, all we know is point C is on the parabola, so that's the function I got to plug into. It's parallel to this line, but it's not on that line. So moving on. So anyway, so if you plug that back into the original function of the parabola, you would get the y coordinate to go with it. Moving on to the last part of this question. So now find an equation of the line that is tangent to P at C. So we already know at point C, we have the values of that point. So one we just did. So we knew the x coordinate was the 5/2, and we plug that back in to get the y coordinate, which came out to be 0. So now moving on to this. So the equation of the line, as always, means point slope. So we have our point. We already figured out too that the slope was -1. That was how we got this guy, was by using a slope of -1 at point C. And so we already know everything we would need to get the equation of the line. So now you're back into your basic y minus y equals your slope times x minus x. And then you could just do a little distribution on that in order to get the equation of the line. All right, moving on to number 4, the second part of this assignment. We'll be doing those other ones later on down the road, so when we get into part 2 of chapter 7. So we're going to be looking right here at number 4. So show that y equals 3 is the asymptote of the graph. There we go. So you got two asymptotes here. The vertical asymptote comes from this idea right here that that's supposed to be does not equal 2. The vertical asymptote comes from this concept right here. X cannot equal 2 because that would create an undefined function because you can't have a 0 in your denominator. Anytime you set your denominator equal to 0 and solve, that always gets you your vertical asymptote. But this one is asking for a horizontal asymptote, which in a rational function like this, remember there's like 3 different ways you could have a horizontal asymptote. Anytime these exponents are equal, we simply divide the coefficients. So in this case, I have the 3x on top, I have the 1x on bottom, and so all we're doing here is because those are the same, I can just divide those terms to get the horizontal asymptote of this graph. And so that would be sufficient in this case. That's an accepted way of getting a horizontal asymptote. And so that works for part A. So find the vertical asymptote. That was what we already talked about right here. Setting your denominator equal to 0 is going to get you the vertical asymptote. So that was part B. So the coordinates of the point at where the asymptotes intersect, well, real simple. This was the x equals. I should have written this one as an equation, y equals, the way it was written right here. So you got your x equals 2, you got your y equals 3. So those lines would obviously intersect at the point 2, 3. So there's point P, where those two lines would intersect each other. So the points of intersection of the graph and the axes. Anytime a graph intersects an axis, that's that's what we call an intercept. So that would either be an x-intercept or a y-intercept. So, you know, if you are on the x-axis, meaning you have an x-intercept, anywhere you're on the x-axis, y is 0. So the way to get the x-intercept is to make y equal 0. So if I set the entire function equal to 0, this is going to give me the x-intercept. Obviously, if I multiply the denominator over to the right, 0 times anything is still 0, so really all I have to solve is the numerator equaling 0. That should always give us the x-intercept when we do that. So in this case, if you did 3x plus 4 equals 0, subtract the 4, divide by 3, and you're looking at negative 4/3 for the x. This one specifically says points, so I would write that as an ordered pair just to be safe. Whenever it asks for a point or a coordinate, they are looking for an ordered pair. So I would write that as an ordered pair for the x-intercept, and let's do the same thing for the y-intercept. So anywhere you are on a y-axis, that means x is 0. So if I sub in a 0 for x, all I'm going to be left with is 4 over negative 2, which is negative 2. So we plugged in a 0 for x and came out with negative 2. So there's the other intercept. So you got your x-intercept, you got your y-intercept. Again, it's safe to write those as ordered pairs, especially because it says points. Or if it says coordinates or something like that, that's a safe way to go. So little details and directions, they always matter for like a test question. So moving on down, so show that the derivative is equal to this. So this is, again, one of those cases where it's a show question, so you got to show the work. Can't just be done on a calculator. Even if you did know how, it would still be pretty hard to do this in a calculator anyway, but nonetheless, it does say show the work, so we got to show that, but it's also specifically giving us a format for the answer. So we got to make sure our answer gets into this format. So, and I'm going to talk a little more about that here in a second, but for part E, so we're going to show that the derivative equals that. Hopefully, just a little recognition here that it's set up as a fraction, so we should be using the quotient rule in order to make that happen. That's something you always got to recognize moving forward, is when to use the quotient rule and when to use the product rule and chain rule. So those are three things that will come up for the rest of the year that you always need to recognize when they come up. So in this case, using the quotient rule, we're doing the bottom times the derivative of the top. So the derivative of this would just be 3 minus the top times the derivative of the bottom. And you can see in this case the bottom derivative would just be a 1 because of that term right there. So we'll just show that. Remember, it does say show, so we want to show all the work for this guy. And then you got the bottom squared, so there's your x minus 2 squared. No need to FOIL that out because they specifically said they wanted in this format, so we don't want to change that. So we should just be able to do a little cleanup on top. Show the work. It does say show, so it's important to show as much work as you can. Distribute the 3. Over here we're looking at, let's distribute the negative, so minus 3x minus 4. A little cleanup on that. So negative 6 and negative 4 are going to come together to make the negative 10. And there you go. We showed the work to get the derivative into that state. So this is a really common thing for IB to do because obviously this answer is now going to be used in the next part of the question. So they like the show questions because they still force you into showing the work for how to get this answer, but the real issue for why they do the show questions is because if you need this in order to get the next part of the problem, well, if you get this part wrong or if you can't get the derivative, you're done for the rest of the problem, and now all the points are gone for the remainder of the problem. So by them kind of giving you the answer in a way, it now allows you to move forward with the question. Even if you didn't know how to get the derivative, you can at least now use it to do the next part of the question, so you would only lose points for this part. Anyway, find the equation. So hence, meaning we're now using that answer to find an equation of the tangent line at point Q, and they are giving us an x coordinate. As always, you're looking for the equation of a line, so it means we need a point and a slope. Get a new sheet of paper for you. So as far as the point is concerned, all we know is the x coordinate, which means we need a y coordinate to go with it. And as always, you will always get a y coordinate from the original function. So if you take x, plug that back into the original function, so I'm going to put a 3 here and here, that's going to give me a y coordinate. So on top we had 9 plus 4, which is 13. If I put the 3 on bottom, I just get a 1, so 13 over 1 is 13. So there we go, we got the point. Now that's point Q, so all we need now is the slope, which of course always comes from a derivative. So if I take my x coordinate, plug it into the derivative, I can get the slope. So if I take my 3 and plug it in right there, obviously 3 minus 2 is 1, 1 squared is still 1, so I'm left with just negative 10 as my slope. And it does not say normal. That's something I'm just now in the habit of checking for, so you should too. So it doesn't say normal, so we're just going to stick with our negative 10, and we're just going to throw that into our gradient function. So again, here's the one that comes up in your formula packet. They call that the gradient function. We would know it as point slope. I'm always going to take my denominator, multiply it over. So usually when I do these, I just jump right into that step, and I would actually do this on my very first move, is go right to that format. But anyway, let's do a little cleanup on that. So distribute the negative 10. So that's going to become plus 30. We're going to add 13 over, so that brings us up to 43. So we got our equation of the tangent line at point Q. So moving on to G, so now we got a tangent line at point R, and it's parallel to the tangent line at Q, and of course we know parallel lines mean the same slope, so we're going to have the slope of negative 10, which we just used. Point R we don't know anything about yet. All we know is a slope, and of course whenever you're working with a slope, that means you're working with a derivative. So if we take our derivative and set it equal to the slope of negative 10, we can now solve for the x coordinate. So I'm going to take my denominator, multiply it over to the right. Let's go ahead and divide both sides by negative 10 just to get some easier numbers to work with. Let's do a little distribution on that, or FOIL. So x squared minus 4x plus 4. Let's bring the 1 over, make it equal 0 since we're dealing with a quadratic. And most likely we can factor these guys. It's pretty rare they give you something that's not factorable and you'd have to use the quadratic formula on. So looks like in this case we can use the negative 1, negative 3. So x equals 1 and 3. So we got x coordinates. So one thing it told us on this was that the point R, or tangent line at point R, is parallel to the tangent line at Q. So that means they share common points here. So as you notice, we came out with 2 x coordinates. The 3 was obviously for point Q, which must mean that the other guy, the 1, is now for point R. So for this guy, we now know the x coordinate for point R is 1. So we're going to take our x coordinate, plug it back into the original function as always. So if we stuck a 1 right there, we'd be looking at sorry, a 1 right there, we'd be looking at 3 plus 4, which is 7, over negative 1, which gives us a y-coordinate of negative 7. So we now have point R. All we need is a slope, which we already have. This one just asks us for point R. We're not looking for an equation of a line, so I just said the coordinates of point R, which is what we just came up with. So last part of this, for part H, says show that P is the midpoint of QR. So a couple reminders, we had point P earlier on, which we found in step C, and that was the coordinates 2, 3. Remember, that was where the asymptotes intersected. So we got point P, we got point R down here. We're also involving right now point Q, so let's just write that one down. So we got 313 for point Q. And so this one is asking, we got another show question. So it says that show that P is the midpoint of QR. So if we look at the coordinates for QR, midpoint, right, is where you do the x plus x divided by 2. And you do y plus y divided by 2. So there's our setup for midpoint. So this is how we show. This is how we show the work. So obviously 3 plus 1 is 4 over 2, which is 2. And 6 over 2 is 3. And so we are showing that that equals point P, which was also 2, 3. And so there you go. We showed the work for showing those guys were equal. And that was it.